to the cloud, right? Not to a computer.
Okay, good. Okay, welcome everyone back online. Unfortunately, we were unable to convince anyone for the rest of the term to actually come and visit us. So we'll have to switch back to online talks. And this is our first online talk by Petr Koroteev, who is going to tell us about q-Opers, QQ systems, and Bethe Ansatz, which is going to be the second part of previous talk from last term. So please take it away.
Yeah, thank you, Miroslav. Greetings, everyone. So, yeah, like I would have come, of course, but yeah, I think the reason why we're online today is because of the school holiday. Yeah, that's right. So Columbus Day or Indigenous Peoples Day. Yeah, yeah, my daughter is off school today as well. Yeah, so they can hear. Okay, yeah. So this is part two. So Peng asked where's part one. Part one was given by my collaborator Anton Seitlin last summer. So also in the seminar, and the links are available on the website. So I will do a quick review, and then we'll report on the new progress that we have had recently. So it's been a well, almost 5-year project right now, which we're very excited about. My primary collaborators on the right, so it's Anton, Edward Tranquil, and Daniel Sage. So Anton and Dan are Louisiana State University. And well, Edward is ours, of course. And then, so Anton's talk was, so he primarily covered this paper that we wrote together, all four of us. And sort of since then, Anton and I, we produced some more interesting results, which are in some sense applications and the further development of this space of q-Opers and how they're connected to integrable systems, to quantum geometry, representation theory, geometric lengths, and other stories. And then I put this paper that I did with Tsekin and 2 other people. So Smirnov, who was here as a postdoc at Math Department, and Peter Pushkar, where we studied a quantum equivariant K-theory of some quiver varieties, and we found an interesting connection between this K-theory and the spectrum of some many-body integrable systems. So that served as a, at least for me, I'm not sure about the others, but for myself, it was the main motivation to keep working on this in this direction. Okay, so primarily today I will be talking about, well, I will start off the ground from this paper and then tell you about these generalized miners as applications to quantum cluster transformations, which some people are working on quite a lot. Okay, so it's a big story which connects to many facets of mathematical physics, or how Greg Moore calls it physical mathematics, which is essentially it's like using string theory to prove mathematical theory, right? So that's what physical mathematics is. So you can think of this as an example of that. So as I said in the previous slide, the first point here would be to study it's a new approach to quantum integrable systems using quantum geometry. So quantum programmology, quantum K-theory. I would probably say that the first kind of important result in this direction was by Giventhal and Kim, right? So when we studied the spectrum of quantum Toda chain and connected it to quantum cohomology of the flag variety, right? And so in a sense, our construction in these two papers sort of followed by formalism developed by Okounkov, and he himself based it on works by Chekhan, Fontanin, Mulik, and others. It's sort of, in a sense, it's a generalization or extension of that first result by Giventhal and Kim. Sort of another motivational part, at least for physics, for physicists in the room, is this famous BPS CFT correspondence, which as a subset includes the AGT correspondence, which was sort of pioneered by Nekrasov and Chitashvili in the late 2000s. Yeah, so I'm not going to talk about much here because this is essentially it's a math talk. But, you guys, I talked about this before in different seminars. Okay, next item here is geometric q-line length correspondence, right? So it's a q world, which we all know and love. So instead of D modules, we have difference D module, right? Instead of differential operators, we have difference operators. So everything, yeah, instead of conformal field theories, we have some, we have something else, right? Which is, not conformal anymore, but because the symmetry is bigger, like it's different. This is what Mina was referring to in her last talk, I think, right? So there was a paper by Mina, Edward, and Andre when we talked about the equivalence between conformal blocks of two different quantum groups, right? So the double deformed W algebra, two-parameter W algebra, and the quantum affine algebra, right? And in a sense, the kind of my story today will be the detailed analysis of what happens at critical level in that correspondence. Okay, and one more point here is this, which is kind of, somehow it goes on and off. So sometimes it's quite popular. People talk about this a lot, and sometimes it's not so. It's not so famous. So this is so-called ODE IM correspondence, which was developed by this gentleman. In a nutshell, they look at the monodromy properties of certain differential operator and find that so if you study monodromy matrix of some differential operator, you uncover this QQ system, which I'll talk about later, for different integral models. So the ODE is just some classical differential equation, and then its spectrum, right? Its spectrum contains in itself, in other words, you can describe the spectrum of this ordinary differential equation using a quantum integrable system of a different type, of some spin chain type. We don't have much to report on this yet, but it's in a sense it's a work in progress. So we hope to we start working with Edward and Andre and Anton as a follow-up. Okay. Any questions so far? Okay. Yeah. So it's okay. Anyhow, so I don't want to talk about every point here, every 4 points. I just wanted to start with this one, which is really close to my heart. I could talk about my favorite spaces and stuff, and then we'll go to q-Opers. So very briefly, so how this new facet of integrable models appears from quantum geometry. So you study Nakajima quiver varieties, which is this certain Hamiltonian reduction of the spaces of quiver representations, right, in the presence of some stability conditions. And you studied the moduli space of quasi-maps from CP1, right, which is subject to this equivariant sister action to that space. And then they're called quasi-maps because they're not honest maps, but rather they map, so they provide maps to an open subset of the quiver variety. And then essentially you need to land on a stable locus in the quiver variety, so which is sort of derived from the data of the ranks of the vector space, dimensions of the vector spaces here. And then for a quiver variety, you can study tautological classes, tautological line bundles, and you can tensor multiply them and multiply by the duals. All right, so that's classical K-theory. Then you can study the equivariant version, you can localize it, and the space of quasi-maps provides you the quantum deformation, which is sort of for every classical class, say tau, you have a quantum class, this vertex function of tau, which is a certain K-theoretic push forward. I'm not going to talk about the details, but essentially it comes into, you need to do some equivariant integration in the moduli space of quasi-maps of each degree, right? You need to impose certain non-singular conditions at 0 and at infinity on CP1, right? And then you compose, basically you have quasi-maps which are non-singular at one point, and then you evaluate the quantum class at the other, at the opposite pole. Then you take a K-theoretic push forward, do evaluation, And then you take a sum over all degrees of the maps, weighted with this parameters z, which are nothing but the scalar parameters corresponding for each vertex, each node of the quiver. Right, so it's a formal expansion, formal sum in those scalar parameters, which is the quantum class, right? And then you can prove the theorem that if you define everything properly, then this quantum K theory is an algebra. So it's an algebra with a unit, right? Which is a deformation of the tensor product of those bundles in every degree. Okay, so this is an interesting story on its own. It's worth probably the whole course, and I think Andrei Yakonkov gave one, right? So maybe several. So I refer you to his lectures. Now, what I'm interested in here is that if you look at this formula, right, and take the sort of saddle point limit, saddle point approximation, which corresponds to setting q to 1. Remember, we live in q world, right? So the classical limit is q goes to 1, not q goes to 0. So q to 0 in a sense is highly singular. Then you'll get this v will behave like exponential to some function w divided by log q, right? And then this sort of, if you look at the w, you find that this is the potential or the Yang function for xxz beta Ansatz equation. Okay, so this is by now it's a very well known and established story. Then you start studying these functions in more detail and find that they satisfy interesting difference equations. Again, we live in a Q world, so all equations are different. And then there are two types of those equations: invariant parameters and scalar parameters. And so Andrei call them either QKZ, quantum condition logic, or it's a dynamical equation. Now, what Anton and I did, we had a sort of we looked at them from the point of view of sort of integrable systems. And it turns out that if you take the fundamental vector solution of the QKZ equation, and sum all the components for certain weights, you'll get a new function, and that function satisfies a simpler equation, just one way. So it satisfies family of equations, but let's just look at one of them. So there's a famous integrable system which is invented by Rosenars and Schneider. It's called Trigonometric Rs Model. So and it's a quantum difference integrable system. Quantum operators, they look like this. So if A's are equivalent parameters corresponding to the framing of the quiver, and P is the shift operator, which shifts the ith variable, ith in this case equivalent parameter, then the vertex function for trivial class, when tau is equal to 1, satisfies this difference equation. So the eigenvalue of the eigenvalue is given by certain symmetric function, and then there's just not one equation of this form, but as many as in this case n, as many particles in the TRS model, or whatever the rank of the quiver is.
Peter, so you're studying a gauge theory partition function on like a disk times a circle.
Yeah, correct. So
with no insertions, and so the equation you're writing here, is this exact, or it's in the limit q goes to 1?
Good. Okay, so yeah, I think right. So when you do this, you do it exact, right? So you do limit to get the Yang function. Yeah. So okay. This comment was only about this part. Yeah, correct. So when I'm talking about, so this P is a quantum difference operator. So Pi acting on f of Zi is equal to f of Q Zi. Yeah. So it's a full-fledged difference operator. It just to make connection with the xxz, I just said that you need to take the classical limit.
I see, and so P is shifting the scalar variables.
There are two frames. I apologize. Yeah. So let me do it again. So as you know, there are two frames, right? There's TRS in Z variables. There's TRS in A variables. And on this slide, I mean TRS in A variables. So it acts on the equivalent parameters. Shift operator acts on equivalent parameters like this, right? And here we are looking at the dependence of the vertex function or the partition function of the equivalent parameters. like, you know, there are two types of equations, right? There's QKZ, which is the monodromy, right? An equation for psi, and then there's a dynamical equation. So then in one of the you act on Kähler variables, in the other you act on invariant variables. And sort of that's sort of Andre and other Andre will sort of always they emphasize that in their big paper that there are two equations and you should talk, like it's important to consider two of them at the same time. Okay.
So what does a little t mean?
Little t?
Yes.
Oh yeah, I think it's in this case t is t. There's a good, so there's a, so the way this q-varieties work, that it's the cotangent space, cotangent bundle to the space of representations of the quiver modded out by the action of the gauge group. And then in this cotangent bundle, there's you can scale the variables in the fibers. So that's the equivariant parameter that dilates the fiber. Yes, yeah, that's a good question. So sometimes, most of the time, it's denoted with h bar, and I think in this convention, if you use the h bar notation, h bar is t inverse. Okay.
And you have such equations in which generality? Sorry.
Yeah. Okay. Mina, go. What's the question?
You have such equations in which generality? You know.
So these equations you only have for type A, right? You can, if you play with this orbifolding tricks, right, by folding the Dynkin diagram, you can probably do it in all classical groups. You can probably do B and C as well. So at least there's something which is called B type and C type, or even BC type Magdalenic polynomials or Magdalenic functions. Yeah, so yeah, I don't know how to do it for E8, for example. So in a sense, kind of one of the motivations to do Opers is that you want to go beyond this. Like you want to treat other groups and non-simply laced series kind of on equal footing with SLN.
I think Ivan also had a question.
Yeah, what's that?
No, that's good.
Okay. Good, and then finally, so you can ask, what's the deal? Like, is there any other way to know that these equations exist? The answer is yes. In fact, that's, for me, it's the very starting point sort of when I came to this field. So sort of back when I was, I was doing physics postdoc at Perimeter Institute. So we had this couple of papers with David, Matt, and Hitchell, which sort of, we looked at the 3D n = 4 gauge theories, like theories which correspond to this quiver diagram. And we, you can think of TRS eigenproblem either in terms of which acts with the covariant parameters or the quantum parameters as some word identity, right? So if you like, it's sort of in more details, you need to take n = 2 star Yanni-Mills in 1 dimension higher in 4 dimensions, and then you would sort of put it on a segment, like you have a segment with left boundary conditions and right boundary conditions, which are mutually BPS. And then the TRS Hamiltonians, they come from the and then the moduli space of vacua for the 4-dimensional theory is the space of flat connections on the puncture torus. So the monodromy of the puncture is exactly this variable t here, or h bar. And then if you subject it to certain boundary conditions, you would freeze the vacuum expectation values of the vector multiplets to some values, which will later become the TRS coordinates, right? So this TRS, it's sort of, if like TRS comes from the different complex structure. So like typically you get elliptic halogen model from n = 2 star, like in Donaghy's Witten story. But if you change the complex structure to J, from I to J, you'll get TRS model. And then we kind of knew that the TRS model comes from there, and then we did some calculations here and there, classically in quantum theory. And sort of now with my math collaborators, we put everything on solid ground. Okay. Anyhow, so that was motivation. So now the question is, so this leads to this XXZ/TRS duality, which is an example of quantum classical duality. Can we generalize it, right? So like Mina mentioned, we can only do it for type A, right? And maybe for classical groups, but can you go beyond that, right? And second of all, So quiver varieties are quite restrictive. So here you have, when you have a quiver, there are certain inequalities on the ranks on these values, right? So if you have a Grassmannian GR Kn, K should be less or equal than N, right? Otherwise, the space does not exist. But you could ask yourself, well, can you go beyond that as well? So the answer is positive, and that's what this theory of Opers essentially provides. Okay, that's what we're going to do now. Okay, so now will be a review of this construction of G q-Opers for where G is any group. So it's complex, simply connected, simple algebraic group G. So that it doesn't matter, simple-laced, non-simple-laced, our approach works equally well for all of them. So we start off with the principle G bundle over CP1, and then have this map MQ, which just multiplies the coordinate by variable Q, hence the Q connection, the q-Opers. Q connection comes later, right? So now let's pick a Zariski open dense set in CP1, and we define the meromorphic GQ connection on FG as a section of this sheaf, right? So it's the hom OU from FG to FGQ, where FQ corresponds to the pullback of the bundle under the map FQ, right? And then,
sorry, can you slow down? What are you hoping that Opers will give you?
So there are kind of two. So there are extensions / generalizations in two different ways. So first, we can, so when you say X, like in quiver varieties is in a sense, it's a restrictive family of spaces, right? Because of all these inequalities, right? So that K is less or equal than N, stuff like that, right? You cannot have a Grassmannian of K hyperplanes in Cn where K is bigger than N. Like it's an empty space. It is the way you define it, and like I will be able to construct an Oper, which will be some analogous, but in that space of Opers will include, if you don't think about the algebra structure, yes, think only in terms of vector spaces. So this will be Opers, and then they will include itself in themselves quantum K theory of quiver varieties, a certain subspace. So like the space of Opers is bigger. So for given G, so say you take the quiver variety with a, like the Dynkin diagram of the Lie group G, right? And put some framing. So claim is that there are more G Opers than all possible quiver varieties with the same quiver diagram.
But usually Opers give you some sort of approximate. They arise when you ask a question about, say, Q to 1 limit. Right? They don't describe the full thing. They're describing some semi-classical limit of it. Right. So are we back to asking about a semi-classical limit?
Yeah. So right. Yeah. So here, starting from next slide. Yeah. So it will be all semi-classical.
Okay.
Yeah.
And just about the TRS, the claim is that are you claiming that this TRS system is equivalent to this QKZ or the KZ equation?
Yes, that's right. Yeah. So in the QKZ is the matrix equation, right? And the TRS is the collection of n scalar equations. You just repackage
some kind of demodule.
Yeah, that's right. Yeah.
And you can so you claim that one can solve for the vertex functions by solving this TRS system. Is that correct?
Yes, that's right. Yeah.
Okay.
Yeah. Okay, good. So I only passed through like 2 slides and 25 minutes is gone. Okay, good. So then we could cut some corners, right? So so the idea of this several slides is Anton had them. I just wanted to show them again. So I want to introduce what is an Oper, like GQ Oper in full generality, and then I'll give you some examples for SO2, for SLN, and then sort of you'll be able to relate to stuff that you already know or have seen before. But just to show that you can do it for any group, right? And then so basically what is a Q connection is it's a right, it's like a linear map, right, from FG to FGQ. So think of this as the linear operation, which takes values in the loop group, right? So it's G of C of Z, right? It's just the loop group where the loop variable lives on this base CP1, and then sort of we define it on the set, which is the intersection of some Zariski open set with this it's a pre-image under the map M, and then if you have a change of trivialization in this bundle, aka the gauge transformation, or shall I call Q gauge transformation, you have this formula. So if you want to see how to get from this formula the familiar gauge transformation, you need to take some expansion. You need to say that Q is equal to eta some epsilon, and then Taylor expand that small epsilon. And also, you kind of formally need to say that A is exponential to some little a, right? And then do the expansion in this one, and you'll get your G inverse plus G inverse.
I'm sorry, can you say again what's the FG superscript Q is? You define FG.
It's a pullback of bundle
by MQ.
By MQ, yes.
Okay, sure.
Yeah, that's right. So that will be important. So because of the Q, there's a grading, right? There's also a Q grading. So there's like FQ, then there's FQ, Q several times, and so on.
Okay.
And we've taken the limit. So from the gauge theory perspective, you took the limit where this parameter that rotates the disk goes to 1, right? And Q is actually some parameter.
Yeah, I think there's a clash of notations here. Yeah. So what is Q here? What is Q here is just it's in all our papers. It's not changes. So what is Q in Oper? So starting from here. So this Q is what was H bar before, or this parameter T. So this Q, so read H bar, which is the C star action on fibers. Yes, or the 2 star mass. Yeah, that is correct. Yeah. And then of course, like we know in string theory that if you try to sort of geometrize all this, kind of describe theory in terms of some branes, then both will have some C star actions, right? So if you turn on omega background, it acts in the field theory directions, and this H bar, it acts in the complementary directions. Okay, now what is an Oper? So an Oper is the triple of 3 objects, right? So you take the bundle, the principal G bundle, the Q connection. So FG with A is the Q connection. And then there's a reduction on the, so there's another bundle FB minus, it's like a flag. It's a reduction to the Borel subgroup, which I call here B minus. So as you know, there are 2 Borel subgroups, B minus and B plus. And then I choose to pick the reduction on B minus. And the Oper condition here means that the restriction of the Q connection on Zariski open density U, so A from FG to FGQ on this U intersected with the pre-image of U on, under MQ, takes values in this double Bria cell. So C here is a Coxeter element. So you take while group for your group G, right? And then you take the product of all elements in the while group in some order. So just pick any order that you like and take the product. So call this Coxeter element C, right? And then there's a notion of double Bria cell in linear algebraic groups. So we take it's a B minus. So if you have an element W from the while group, you can sort of sandwich it by 2 Borel subgroups. And in this case, I do the B minus. So I demand that the this Q connection takes values in this double Bria cell. So basically, so think about if you kind of using some SLM language. So think of B minus as a lower triangular matrices, and W is just well, it's like a matrix with ones on top of the diagonal and 1 in the bottom. Okay, so if this looks a little bit abstract, I'll show you soon the example for SL2. So that locally means that you can take that in terms of like explicitly, it looks like this. You take phi, some complex function, to the power of the Cartan alpha I check times Si. So you keep the same product as in the choice of the Coxeter element, and you sandwich it by 2 elements from unipotent radical. So n minus, I remind you, it's the commutant of B minus. Okay. So we'll make this formula very explicit in terms of generators, in terms of Chevalier generators of group G. And the sort of the only ambiguity, if in a sense, will be the choice of the order of those reflections. Then eventually we'll prove that the QQ system and the Bethe equations, they do not depend on the choice of this order.
Sorry, can you explain a bit the motivation for the Coxeter element? Like, and what's the dimension of this double Broussard cell? Like, it's not the open cell. It's,
yeah, I mean, this it's also, if you take there's this, in broad decomposition, you can take union over all elements of Weil group, and you'll get your group G, right? So this is just one particular element. So like I take,
right. So why this element?
Well, it's a certain choice. Like the it's the well, how should I say it? Well, you'll see. It's the
okay, maybe I will wait and see how it's used.
So think of, let's take maybe a simple example like SL2. So you just have one reflection, right, in the Weil group. So what I want to do is I want to have so like in SL2. So moving ahead a bit, what is the Oper? So you take a bundle, like a vector bundle of rank 2, and there's a rank 1 sub bundle, right? And then the Oper condition is that the sub bundle is isomorphic to like the restriction of A on the sub bundle. So there's an isomorphism between sub bundle and this factor E model Q. So what this element does, it's what swaps around this space and that space. Yeah. So if you have just one reflection, if you have many, so that's the way to kind of to generalize it, to package it.
Okay. Okay. Thanks.
No, it's a legitimate question.
So in the continuous world, right? What one wanted was some Opers with trivial monodromy, which meant that if you go around punctures, that this thing comes back to itself. So it tells you what kind of object.
That's right. Yeah, so those will be like Q analogs of those Opers with.
So it's just a Q analog of the trivial monodromy condition.
Yeah, so they'll be trivial monodromy. So we'll add some decorations, we'll add singularities and the twists, but it will still be like the trivial monodromy condition. Yeah. But please make sure, I mean, so those are like Opers for G, not for affine G. So those which appear in this ODRM correspondence, what Francis studied, those are for G hat, right? So I don't do affine, I just do Lie algebra, like the Lie group itself. I mean, there's no like, I want, okay, at least until sometime later, there will be no affine affinization whatsoever. Yeah, okay. Other questions? Good. And now one more important part is the part of the definition, which actually allows us to compute anything. These are Miura Opers, Miura GQ Opers. So Oper was a triple of objects FG, A, and FB minus, but now I'll also pick another flag, FB plus, right? So it's the reduction of G bundle FG to the opposite Borel subalgebra, subgroup, excuse me. And now I demand that this reduction is preserved by the Q connection, right? So in terms of linear algebra, just some invariant subspace over here. Now, you can ask, do these guys exist at all, right? So, well, so in the example of SL2, which Ben just asked me, the answer is of course yes, right? So there is this L, and then like, so if L is generated by 0, 1, right? Then this guy is generated by 1, 0, right? But for general group G, you cannot, it may not always be the case. So what you need to be shown, and I think in the interest of time, I'll keep the discussion here. I'm just going to quote the theorem that it needs to be shown that these two flags, this FB minus and FB plus, right, they are in a what is known as generic relative position for some Zariski dense set V inside the base P1. And there's some technical details here, which I think we can gloss over. Essentially, like you would identify the while group for G with this double quotient, G mod B minus and B plus, and then you require that for any element in the scheme, right? The element of the while group G assigned to this element is equal to 1. So it's like you always get the trivial element from the while group. So in other words, mu opers exist, and it's a reasonable thing to talk about. So think of it as the Oper with the additional structure, where there's a flag of subbundles which is preserved by the Q connection. Okay. Yeah. So
except that your setting is much less mysterious than what he's doing, right? I mean, if you're studying the Q world, you're studying gauge theories and D-branes, where you don't have to be guessing.
You said with whom are you comparing this?
Well, I mean, M theory setting is far more mysterious than the setting you're working in, I would think.
M theory leads to what? To which kind of?
What I'm trying to. Oh, sorry, go ahead.
No, sorry. Can you say it again? I didn't understand the premise of your comment. Yeah. Mina,
your story does not come from M2 branes; it comes from D3 branes.
Yeah, that's right.
Which are less mysterious. You should be able to derive these statements. You don't have to, motivate them by Costello's. Rather, what you should.
No,
you should be able to understand exactly and then tell Costello why his things are true.
This is
not the other way around.
It's a book on linear algebraic groups. It's simpler than that, right? it's from Humphreys. But I think you told me some time ago that everything you can do in M theory, you can do in perturbative string, as far as this.
No, the other way around. M theory is hard to understand. Perturbative string is fundamentally.
But like in terms of applications, at least what comes, as an experience, like usually everything you can do in M theory, you can restate it in a different language in perturbative string theory. But okay, maybe it's another. Okay, so let me continue, and then you can discuss more the M theory. Okay. Muras, and then these are the structure theorems, which are they're pretty hard to prove. They're technical, but they'll allow us to actually write some formula for it, right? So in particular, so let me skip the first one. I'm just going to give you that so in other words, well, yes. So first, the Q connection for the Mura GQ Oper on P1. You can see that there exists a trivialization of this bundle on a dense subset, which takes this value, right? And so now it's this n minus the unipotent radical, and there is some function to the power alpha check Si. Again, I just I pick the order in the while group out of blue, and I keep this order. So we'll talk later about what happens if you change the order, right? And then intersecting with B plus, and if you write down the formula, it looks like this, right? So this Q connection has this form. So it's so G is some function here in the loop group to the power of alpha check exponential to the raising generator EI multiplied by some other function. So if you like, this is how the Q connection looks like. And as I told you before, the ambiguity comes from the choice of the product over here, which comes from my initial choice. Now we need to add 2 more ingredients in order to have the full story. So these are singularities and twists. So we consider the family of polynomials lambda I, as many as the rank of the group. So we say that we have a GQ Oper with regular singularities, and analogously, Miura GQ Oper with regular singularities, if it takes this form. So instead of, so we have a function which actually can have zeros at some points on CP1. So singularity of the Oper is it's the point where the connection becomes 0, right? It's like that, right? So it's non-invertible anymore, so it's singular, right? And then you would be able to write the Q connection explicitly like this, right? So it's same formula from before, and now adopted with proper normalization. And here, those functions GI, they take values in a C of Z star, so some non-zero rational functions LC. And now Oper is Z twisted if this connection is diagonalizable to a diagonal matrix Z. So Z is some regular semi-simple element inside the cartan, which is in turn is the subgroup of the loop group. And so there is a gauge transformation, a Q-gauge transformation G, which satisfies this this equation. Again, so in terms of SLN, think of just some diagonal matrix with the with some non-zero eigenvalues. And finally, the Z-twisted q-Oper is Miura if that trivializing element belongs to the Borel subgroup B+. Okay, so so this statement is more restrictive than this one, right? So if any G it works, that's good. But if it's if you only pick G from the Borel, from the opposite Borel, it's more restrictive.
And can you, when you say you're adding singularities, can you add singularities at arbitrary points of the P1?
Except 0 and infinity, yes.
I see. Okay, good. Mm-hmm.
So you should actually think about like a cylinder. So you take out. Okay.
Right.
Good. Moving on. Okay, so what are we doing here? Good. Now, so how do we compute anything here? So it turns out that so this language is not very convenient for computations, although we do have some explicit formulae. In order to have to make it more explicit, we need to introduce a new notion of the Oper, which explicitly deals with the SL2 subgroup of G, right? Because for SL2, it's very explicit and it's very simple. Sort of, and this is what we're going to do. And this is where this Plucker formalism, Plucker embedding comes in. So so let's take VI plus will be the irreducible representation G with highest weight omega. And then we take a line Li inside of Vi, which is stable under B plus. So these are the standard Plucker relations for, so if you have any two integral dominant weights, lambda and mu, right? So you have L of lambda plus mu inside V of lambda plus mu. So this is the image of, if you tensor these two line bundles, if two one-dimensional vector spaces, right? And it will be a subset of V lambda tensor V mu. So this will be the image. So L lambda plus mu will be image under this canonical projection. So V lambda tensor mu goes into V lambda plus mu. So you just add those two dominant weights, two spins together, right? And conversely, so if you have a collection of some lines with the dominant weights lambda, which satisfies Plucker relations, there exists a Borel subgroup of G such that all those lines are stabilized for all of those weights, right? And in a sense, the choice of B, choice of this Borel subgroup is equivalent to a choice of this B plus torsor in G. As when we try to make the description of this Oper explicit, right? So when we take the restriction of Fg on subset, we'll always have this. We have a choice of this B plus principal bundle, right? Which trivializes. So this is what we're going to do here. We'll use this idea to take a two-dimensional subspace V sub I, which is generated by nu omega I. It's the highest weight vector, and another vector which is obtained by action of the lowering generator Fi nu omega I. So this 2D subspace is spanned by V omega I, the highest weight vector, and then a simple reflection. And right now, because Fi kind of moves it down, right? This subspace is invariant under B plus over here. So this will be the kind of the space where from which we'll construct our SL2 Miura-Plucker Oper. So just, if it's not familiar to you, just think of this two-dimensional subspace. So highest weight vector, the weight omega, and a two-dimensional subspace, which is B plus invariant.
Now, sorry, can I just ask you this? For type A, you have exact solution to the problem you want. So using this TRS. So you're saying if I have just a general quiver gauge theory, you're not going to have that.
I don't think I have even a quick quiver gauge theory. So say you have a quiver like this, right? Can you describe a gauge theory? Like what's the triple link even means, right? So with Hanani and friends, we tried to make sense in terms of this orbifolding just by starting from the gauge theory. But again, you get something not very sensical. So gauge theory works only for simple laced kind of.
No, so for non-simple laced, string theory tells you what you should be doing. So it's just that you don't have a, it's not a gauge theory on S1 times disk. You need some kind of twist.
Yeah, right. So what we call H twist, or what Nikras, Kimura, and Peston call some other twist, right? I mean, there are tools, right? But this construction is universal. So from the point of view of this approach, G2 and SU2 are the same. It's like you don't need to artificially twist anything. So moreover, no, Edward Frankel is now writing a paper with collaborators. So he should appear this week. So he's with Hernandez and Reshetikhin. So they'll be discussing exactly this issue, right? So they'll be discussing how Bethe equations that are obtained from folding, how they differ from these other equations that were appear from the W algebra, right? So if you have, say, studied this Langlands for W algebra, like for G, where G is non-simple laced. So there is a difference. And I think we discussed it last week with
Sure. I suppose I have lost track of what's the starting point. Is the starting point a gauge theory? Is the starting point
Okay, so first slide was motivation. So when you have q-variety, you have gauge theory. Now I abandoned that. I said, okay, let me just study some classical object, which is Oper, right? So we essentially bundle some conditions, and then I'll show you that this Oper is equivalent to this QQ system, DFU, right?
And physically, what does this mean?
Well, when it's a gauge
physically
theory,
what are you doing? I mean, okay, so it's something you can define and it's a good math definition. Why is it, why do you as a physicist understand why it's a good math definition? In other words, why is that a right story to tell?
It's a math paper. Yeah, so it's like I think at this point physics stops. It's like no, it doesn't stop. It just, you can still try to make sense of it from string theory, but the questions you should be asking is like how to get these equations as opposed to the other equations from some folding. Or
do you understand that these are natural physically or not?
I think these are more natural physically than the other Bethe equations for non-simple laced groups. And the reason why, because you get those from folding. So if you take your H background, right, you'll get our equations, not the other ones.
Yeah, I'm not sure what how you get the other ones. There's, I mean, it's just some equation that Reshetikhin wrote down at some point. So
yeah, that's right.
I see. And you're saying that yours is better.
In a sense, it's more physical, yes.
And okay, and will you explain to us why in the end?
Take your conformal block, right, with for non-simple laced, and then take the saddle. So we'll get equations which are, these ones, right? So see here, we have in the right hand side we have something to the power of the Cartan matrix, right? So it will be something like squared or maybe cubed. Yeah. So these are the folded equations. Okay.
And just one more question. I suppose it's a question for you and for Miroslav. Okay, I suppose for you, the Q plus and the Q minus objects, do you know what produces them, like even in a simply laced setting?
Yes, absolutely. So that's okay. So since that's, let me go a little bit ahead. So the, okay, yeah, I kind of expect this. I have all things. So sorry, I didn't mean to. No, that's fine. That's fine. That's fine. Tell me that you'll explain it to me, but okay. I think I have like slides for like 3 lectures, like yourself. So, all right. Anyhow, so the okay, so let's talk about what's it? Cyber-Clag transformations. Okay, so you have say take a queer gauge theory, right? Yep. Then you have a Q polynomial for every node, right? So like so there's Q plus. Right, so zeros of Q plus are just as beta roots, right? These are the VAF expectation values, blah blah. So these are physical VAFs, right? Which sit in Q plus. Now you can ask, what are the other guys, right? And then just Q minus. So they're not only Q minuses, but there are also Q minuses for like several minuses. You can keep doing those mutations, right? So the claim is that you can start off with Q pluses, right, and formulate your theory with them. And the other guys will be the, so we call this quantum Backlund transformations, but in physics language, it's Cyber-Clag dualities on some nodes of the quiver.
And Q minus is also obtained from Q plus that way?
Yeah. So let me show it here. So it's called quantum backlog. So you start off with a sets of q pluses for every vertex, right? And then you do this slide explains how to mutate the q connection for the Oper, but let's forget about it for now. So and then you mutate on ith node, okay? So the q plus is replaced by q minus.
I see.
And then the twist is replaced by this expression, right? And now you can imagine doing cascades, right? You can imagine I mutate this here, then I mutate there, then I mutate there, and you mutate everywhere in some order.
I see.
So we claim that this way you will have recovered all q polynomials. And there are not, so if you have a quiver gauge theory with rank n, like n-1, n like here, so that there are n plus 1 actually. There are, for this kind of theory, there will be n plus 1 q polynomials which are obtained by these mutations.
Okay.
And then sort of, again, geometrically, because we started with Opers, those will be literally the components of the section of a sub-bundle in the Oper construction. So like, we say, okay, you take this one-dimensional sub-bundle, line sub-bundle, and then you have the flag of sub-bundles in this Oper condition, with this kind of stuff that I talked about, and claim that very explicitly these components of the section are just literally these q polynomials.
I see.
Yeah, it's a beautiful geometric story. Kind of, it actually tells you like what QQ system geometrically means.
Very nice. Okay.
So okay, so maybe I can talk about that a bit since you asked. Good. So the let's talk about this. So the SL and q-Opers. Good. So right. So the QQ system, you can write it like this. So those phi's are ratios of q minus and q plus, just divided by q plus everything. And then the right hand side is again, if you divide by q pluses, you'll get this thing. And you have as many equations as nodes in the quiver. Okay, now claim is that the q-Oper condition, so the SLN q-Oper A, right, is diagonalizable by this element V, which lives in the B plus in the Borel, right? Or rather, V inverse lives in Borel, but it doesn't matter. So it turns out that even for this gauge transformation, you can write an explicit matrix, right? You can write explicit matrix whose entries are, again, so see, look at the last column. You have q plus, q minus, minus, and then like just the multi-index means that how many times you mutate depending on which orders. Like there's 1 through R, it's as if you have completed the whole. If you go along the quiver, like 1, 2, 3, 4, 5 till the end, right? And here, if you stop at the second node from the left, here if you stop from the third node from right, and so on. And then, yeah, these are just some ratios. So, like, even the gauge transformation is very explicit.
Well, one of the surprise for me from Miroslav's work with Davide is that these Opers were not the brains I had sort of imagined them to be. They had the same effect, but they're not the brains you imagined them to be.
I think in the
it would be interesting to rethink this. Huh?
Are you thinking about Roslin, Krasov, Shatashvili, or some other?
No, well, you know, usually, you know, the way I thought about Opers before is that if you have some their brains in the sort of 4-dimensional space, but just a different plane that you would say if you're studying AGT, right?
Yes.
But there are two sort of obvious sets of brains. One that wrap one of the two planes that are fixed by rotations. They're neither of those.
Oh,
that's what it is. That's what they say, that there's something else, and it's so which we also know exactly in string theory what they are, how to construct them. But I think that might have anyway.
So you think this is something yet different than you expected?
No. You still have Seiberg dualities and all things like that. It's just that the brains according to them are different. They're brains that don't probe the 4-dimensional space at all. They point like in 4-dimensional space. They point like on the Riemann surface.
Exactly. I think I need to understand that better. So I want to understand this kind of brain construction of these Opers to do the ODIM story for the next paper. But like, So can you tell me again? So we have, AGT has the 6 dimensions, and then there are complementary 4. So you think these live in complementary 4?
Yeah.
And it's what? It's some Riemann surface, or so that P1, my Oper P1, it's another 2-dimensional subspace there. It's sort of, and then okay, so let's
they'll I think they'll be associated with branes that say fill the 4-dimensional space, and they're just the extra 4-dimensional space.
The extra 4-dimensional. But you might be using some string dualities. You can rebundle, like have an alternative description, which is.
I don't think so. I think that their picture is very precise. So.
Okay, good. Yeah,
that's what one has to live with.
Let's talk later. Okay, good. Okay, so do I have to talk a little bit? Okay, maybe.
But these are beautiful equations. So this is from your last paper.
So most of equations I'm being showing right now are from. So far I only talked about so the paper with Edward, and then the equations with this the linear algebra. It's from a paper with Anton about the toroidal q-Opers.
So this suggests that the while group action is generating all these q minus Opers. Is that true always?
Yes. Yes. Good. It's true always. Yeah. So just for SLN it's very explicit, but for other groups it's less explicit, but you can still write some formal expression. So this we addressed in the last paper. Yes. Okay, good. So maybe to get everybody back on track, let's talk about SL2 Opers, like folks will. Okay. Let's do SL2 example, shall we? Yeah. So here's what's kind of this duality in a nutshell. So SL2 q-Oper. So when I say q-Oper, think of Q connection, right? So if you sort of more kind of if you want to see this formula, so this is the formula. It's an upper triangular matrix. So remember, lambda has the singularities of the Oper, and G is in this case, it's a rational function. It's a ratio of Q plus shifted by Q and Q minus and Q plus unshifted. Okay, now the condition for diagonalization of this matrix is this, as we discussed, and you want to gauge rotate it to just SL2 Cartan. Okay. Well, you do it like in 10 minutes. And you can find that this is the explicit formula for the gauge transformation, and you can find that G is this function, and then the q-Oper condition is literally equivalent to the SL2 QQ system. Right, so this is the SL2 QQ system. It's twisted, so there are twists over here. There are 2 types of polynomials, as we've been discussing, Q plus and Q minus, with this characteristic shift pattern by a little q, and the singularities, the polynomial lambda, which encodes singularities with Opers, is on the right-hand side. Okay, now where are the Bethe Ansatz equations? Well, so for this we need to explicitly specify spell out the q polynomials and lambda polynomials. So look, now let's talk about singularities first, because it's kind of new for the q in the q world. So think of CP1 without 0 and infinity as a cylinder, right? And then there's a C star action, right, on the cylinder. So for every singularity, you attach an integer, which is here, it's called R sub p, which is like a spin, right? And then you'll have a double product, right? So for every singularity Z sub n, like Z sub p, you will have R sub p worth of, like we have a string, right? You have a string with several, as many as the spin goes, singularities which are differ by the q, by scalar multiplication by q. And then you take the product of all singularities of the on the CP1. So roots of polynomial q plus are Bethe roots. Now there's a standard trick in this business. You need to first evaluate this equation, for example, at roots of q minus. Then sort of this term will disappear, and then you do the q shift and evaluate it on the roots of q minus again, and then the other term will disappear. And then you take the ratio, you'll get this kind of equation, or if you write it explicitly, you'll get this celebrated XXZ Bethe equation.
And who picks R sub p for you?
Say again, please.
Who picks R sub p for you?
Oh, just yourself. Good. So that's where I told you, like, you can pick any. Yeah. So so in this case, like if you were studying pure varieties, right? So then that would in this language would correspond to very particular restrictive choice of those spins, of those weights. you won't be able to, like for the Grassmannian, I think R sub P is equal to K.
Oh, you're picking, oh, sorry. I'm not looking at the equation carefully enough. I see. So their choice of, I see their choice of equivariant weights or mass parameters, which you want to be, which you want to have on a lattice.
Yes,
I see. And once you have them on a lattice, you have this construction. Okay, good. I understand.
Yeah, that's right. Good. In fact, yeah, let's look at a particular choice of those guys, and that connects with the integrable system, this quantum classical duality here. Good. So let's take my favorite space, which is the cotangent bundle.
Wait, but in general, for you have a problem with doubts. I mean, for continuous values of equivariant parameters, you don't have to put them on any kind of lattice.
Oh no!
So you're saying that good things happen when you do?
No. Lattice comes from the yeah. So good, right? So if you have just normal, quill variety, I think all those weights are just one. Yeah. So the lattice comes when you do the degeneration. When you
So explain why are we doing the degeneration? Why are you fixing the equivariant parameters? I thought you.
Here.
Sorry. Yeah.
So the let's look at Bethe equations, right? Because these are Bethe equations for what? For the
sorry, I apologize. Just a second.
I think here there's a typo. There should be so this M is no, that's fine. Yeah, I think it is here, right? So this is it's the Grassmannian of M hyperplanes in CL, I think, and then there are good, right? And then there are L, here. So the Z sub P are the positions of the mass parameters, and then in this case, right? So you would have imposed some degenerations, some resonance conditions, but you don't have to do it. Like, so if you just do it, the most generic situation, all of those spins will be equal to 1. So you'll have just a single product of these guys. You have just Z minus ZP. Yeah. Okay. So in fact, if you do just that, right? Let's see what we'll get. Good. So we take a T star of G mod B, right? So it's of the complete flag in CN. And then, here I have it in Oper language, but basically it's the same as I just said. So then, if you take the components of the Oper section just to be one-dimensional polynomials, so if all q pluses, right? If all q pluses are degree 1, with roots, with some roots, right? Then the Oper condition is equivalent to the TRS eigenvalue problem. So. Yeah, so if you like, so in this example, the cotangent bundle to the flag in CN, right? It's equivariant quantum K theory. It's described by the space of q-Opers for SLN minus 1, for SLN, and for those Opers, the polynomials q plus are all of degree 1. If you take more general polynomials, you'll have something more complicated, which in sense goes beyond the geometry of q varieties. Yeah. So in connection to quantum geometry, those coefficients P, which will later become the Terrace momenta, are the ratios of these q polynomials in origin, which is in turn some interesting quantum class. It's like something like top exterior power of VI with the tautological bundle tensor with the dual for the next node for Fi plus 1. Okay, good. Right. Okay, what did I? Okay, well, let me talk now more about the this Muir-Pluk Oper, right? So, what's the story about calculation of the QP system? So, this Muir-Pluk Oper is the following thing. We take a like I said, there's a two-dimensional vector space, and we associate a GL2 or SO2 q-Oper, which works like this. So A sub I, so instead of one Oper, we have are as many as the rank Opers, and for each I, for each vertex, for each root, there is this 2x2 matrix. And here you see there's a certain product over elements like this. And again, so I continue saying this, the order in this product is given by the order of the original Coxeter element. And then we define this z-twisted Muir-Plucker q-Oper, which is a Muir-Oper, such that for every GL2 q-Oper, the restriction on this two-dimensional subspace Wi, which is generated by the highest weight vector with weight omega, and its reflection Fi acting on this vector is diagonalizable like this, right? So, and z sub I is just a two-dimensional. It's a 2x2 matrix, which is the projection of the twist operator onto this two-dimensional subspace. Okay, and then those Opers, the Muir-Plucker Opers, using those we can actually derive this theorem. We can prove this theorem that there's a one-to-one correspondence between a set of non-degenerate z-twisted Muir-Plucker Opers and the non-degenerate solutions of the QQ system. So here, so zetas are the eigenvalues of twist operator Z, and Xi and Xi tilde are certain products in this order. Okay, we don't have time for proof, but anyhow, so it's basically the that comes from a straightforward calculation, which is kind of possible in this Muir-Plucker form. Okay, any questions here? And then the Bethe Ansatz equations, which you can derive analogously from the QQ system by doing the shifts and then dividing by equations in the presence of other shifts, you'll get these kind of equations. They look pretty scary, but essentially it's the generalization for G to arbitrary group G of the SL2 equations that I showed you before. So here, W's are the roots of Q plus, as we already discussed. And you can see here that on the right-hand side, we have this peculiar powers to the negative AGI. So if it's SLN, then those are equal to 1, right? Because on the super diagonal and on the subdiagonal, the Cartan matrix, you have negative ones. But if you have, for example, G3, or excuse me, G2, you'll have 3, right? Or you could have 3 or 2. And that's how this folded equations, folded Bethe equations work. Yeah, which we'll discuss already. So at this point of the talk, we have established the three-way correspondence between space of solutions of a QQ system, Bethe Ansatz equations, XXZ, these guys. You can see that there's always an adjective non-degenerate, which is just the fact that the zeros of Q plus and lambdas, they should not coincide, and they should not live on the same Q to the Z lattice. If they do, then there'll be some cancellations. But you can deal with that, which is not a big deal. So if you like, you can remove non-degenerate. Statement will still work. And finally, there's a connection between z-twisted Muir-Plucker q-Opers with regular singularities. Now, the final step will be to connect Muir-Plucker. So we want to drop Plucker. We want to just do Opers without Plucker. And for those, we'll need background transformations and these mutations that Mina was asking about.
So the non-degeneracy statement is a statement about what? It's a statement about the 3D gauge you're starting with, or okay, let's say
it's certainly like it's a stereo and omega background already, right? Essentially, the difference of masses should not be integral multiple of epsilon. That's what it says.
I see. Okay.
Yeah. So yeah, if it is, like I said, there will be some cancellations in this equation, which would, in physics terms, mean that some hypermultiplets would decouple. Like it will be, the theory will have some decoupled sectors, which I think is by now understood in physics literature too. Good. So now we want to drop Miura, and to do that, we'll do the this background transformation. Okay, we did this. We do the quantum background transformations. So we talked about the ramifications on what happens when we change Q plus by Q minus. We can ask ourselves what happens at the Oper side, what happens with the Q connection. So let's do the following. Take your Oper, the full Oper, not neuropluker one, the full one, right? And then make the similarity transformation like this. So f sub I is the lowering Chevalier generator, and mu sub I is this function, which cooked up from Q polynomials, which talk to this, like which come from the neighboring nodes on the Quiver diagram, right? So like this. And it turns out that these are the same things, right? So that the switching Q plus and Q minus and the twist in a QQ system is equivalent to, well, you can say it in two different ways. So first, you change the q-Oper by the similarity transformation, or you effectively change the choice of the Borel subgroup, right? So what was B plus and B minus before, now it's not quite. You need to do this kind of rotation, right? You need to change the assignment, what is B plus and what is B minus, because you made one reflection, right? And then you can you can do it all the way, like you can do it as many times as you need. So in fact, if you take the product of this while reflections like this from all of them in some order, take the longest element of the while group, and just perform this mutation transformation in that order, right? So what will happen eventually is that that you will remember, to show that the Oper is the Miura GQ Oper, you need to manifestly we need to write explicitly the diagonalizing element VZ, which diagonalizes Oper to the diagonal element in Cartan, the big Z. So we claim that if you take this, if you do these mutations successfully one by one, no matter in which order, you will have reconstructed this diagonalizing element and the full q-Oper. If you like, you can have your, say E6, E6 Dynkin diagram. So you start from here, you first mutate here, then here, then here, then here, then there, then there. Well, collect all the terms together, and then the diagonalizing elements for each of the Pluker Opers will combine into this big V of Z, which would give you the trivializing element for your E6Q Oper. So every Z twisted Miura Pluker is just Z twisted Miura. And this way we can continue, we can complete the duality diagram. Any questions here? Yeah, so in a sense, this quantum background transformations, they're not just connection with physics, the separate dualities, they're actually an essential part of the construction of proving the theorem. Okay, so I'm going over time. Do you want to listen to me from like 10 more minutes or what? Or do you want to close here?
Yeah, sure. Let's go on for 10 more minutes.
Okay.
Sounds good.
The reason that my older daughter goes to dentist, I need to take care of the junior one like in 20 minutes. So I have some amount of stuff. Good. So now let's talk about this last paper, these generalized Wronskians. So okay, there's again this algebraic construction. So we take the Brouillard decomposition, this biggest Brouillard cell. So every element is the product of, well, composition. It's the Gaussian decomposition of the group element, right? We have n minus, h, and n plus, and then well, so the Cartan, right? If you take the highest weight factor mu omega I plus, then this weight will be its highest vector. So it's just the abstract way to define what the principal minor is for group element G. It's just this this eigenvalue over here. And for SLN, there will be just actual minors of the matrix. Now we want to talk about generalized minors, which are obtained by taking G and then twisting it with this elements U and V. So if U and V are elements of the while group, we have lift of, so you can take the element, you can lift it to the loop group, right? So to the to the group itself, and then because they're defined up to the cartan element, up to the choice of the cartan, and then you do this twist. So those are called generalized minors, and they're labeled by a pair of two elements in the while group. Okay, and if you look at the if you act with the group element G on this weight vector nu omega plus, then kind of it will be an expansion over elements in the while group, and the first term will be like the coefficient in front of the the nu plus omega I will be exactly this generalized minor when u is equal to omega to w element of the while group, and v is trivial. Now, why am I telling you all this? Well, so first of all, I want to. So it's a different, yet another way to describe what is the Q polynomials from the Oper construction. So remember I told you the story about SLN. When you have the flag of subbundles, there's a vector that parameterizes the smallest one, the line subbundle, and Q polynomials are components of that section. Now, this is what we need to do if you want to go beyond the SLN. So if you want to describe those quantum Wronskians, right? For any group G, you need to work in this language of generalized minors, right? And this is what it's done here. So you can show that if you take the trivializing element W inverse V inverse from the q-Oper story that we just talked about, and then calculate its generalized minor like this, you'll get exactly Q polynomial. So see, now it's labeled not with the index, but not only with just one index, but also with the choice of the element from the while group, and that's connects to what we just discussed before, right? So you can take Q plus, and then you can do these mutations in some order according to every element in the while group is a product of reflections, right? And you pick the product of reflections yourself, and this way you're going to get any Q polynomial that you want. Good. And then, well, let's not talk about the proof. So Fomin and Zelevinsky, right? So the cluster people, so they have proven famous relationship between those generalized minors. So it's from their paper of '94, I think. So it's a very nice paper. So there's if you look at the length of permutation of elements U and V, and if they satisfy these relations, then generalized minors satisfy this quadratic relationship. Well, we claim that this is exactly the QQ system, right? So after you identify the parameters properly. So again, you can see there's a characteristic power to the delta to the power negative AJI to the cartan matrix, which hints to the folded equations. Right. So what we proved with Anton is that this is nothing but the generalized QQ system relations. And yeah, so maybe I can show you the punchline. So we introduced this generalized Wronskian, which essentially goes along the lines of q-Opers, the Muir-Kluker q-Opers. So again, there are two vectors, one and the other, which is different by the action of some Foxeter element. And then we require that this generalized Wronskian G, which is just some section of this bundle, acting on one of them, and then multiplied by the twist element is equal to the q-shifted element, q-graded, right? So q-shifted generalized Wronskian acting on plus on this other vector in two-dimensional space. So it's a very similar condition to the Muir-Kluker Oper, only sort of framed in slightly different formulas. You can also add singularities. You can define generalized Wronskian with regular singularities by adding those polynomials lambda as before. So everything goes one after another very analogously. So then Fomin Zelevinsky relations should read like this. So the product, the part of the minors in the right-hand side will have this element C inverse inside them. The others will not. Yeah, and then basically you can show that it's the same thing. So that this generalized Wronskians with regular singularities, the space of those is in one-to-one correspondence with the space of z-twisted Miura GQ-Opers with the same regular singularities given by those polynomials lambda. And you can even write some explicit formulas. So if you take this quantum Wronskian W, then it's shifted by k+1 times q Wronskian acting on this highest weight vector is equal to kind of this product of elements from the so S is the element from the while group, and then you lift it to the loop group, and then sort of you take the product in this order.
And for Min and Zelaminsky, what was their motivation for studying these things? Which world did it come from?
Cluster algebras.
What about cluster algebras?
So they talked about, they need to introduce the coordinates, right? This cluster coordinates in the on a cluster algebra, and then the so these generalized miners, they are so if it's one of the kind of universal kind of gauge invariant choices of this coordinates. It's like you introduce some set of coordinates and there are relations on those. So if you have the like the conditions on the lengths of permutations here. So for these conditions, you have this kind of relation. If this is different, the relations can be more complicated. So it's like a syzygy. You have like the so you want a set of coordinates which will be invariant under the mutations, right? So when you do the cluster mutation, you should have a simple rule which will tell you what happens with the with the rest of the data. Like what's the prescription of how to change this? Well, I guess I'm not remembering correctly. But anyhow, so it's some invariant set of coordinates for in the cluster algebra. It's basically, see, it has explicit description in terms of the while reflections from the while group.
So the while reflections get mapped to cluster transformations?
Yes. Yeah, and these are sort of invariant objects there. Yeah, I think that's the best answer I can give for now. And then so I'm going to give you an example of this equation for SLN. Yes, so we're here. Yeah, so again, this is an example for SL2. So the QQ system that we got is equivalent in this language to the condition that the determinant of this generalized quantum Wronskian is equal to 1. And you can sort of put it like this, like here so this is the condition on the Q Wronskian, right? So S is the reflection, which is so this is element S, right? So S inverse is the S inverse tilde multiplied by the Cartan, right? That's how you do the lift of elements from while group to the loop group. So it's just this element. So it's defined up to lambda, and lambda contains all the singularities. Take the highest weight vector of the fundamental representation, and this is the twist element. Okay, and then well, this is the element W according to the rules. So it has this Q polynomials and lambdas here, which are hidden in the denominator. So the QQ system in this case is equivalent to the determinant of W of Z is equal to 1. And then it will be similar for SLN. So yeah, this is the formula for SLN. So like the element S tilde, the element from the while group, if you take the product of all reflections from first to the last, will be like this. Like we have 1 here and then another string of 1s on the subdiagonal. You can lift it to the loop group. You can lift it upstairs and write formula for the quantum Wronskian, which will have some explicit metrics. Yeah, and sort of like now you can sort of generalized miners will be like actual miners of that matrix. And sort of finally, the last point, very explicitly for SLN, you can write it using this identity which is known since 19th century. So take matrix, square matrix, and calculate its determinant. And now you can do a couple of things. You can remove the first column and the first row, it will be matrix by one size smaller, you can calculate this determinant. So then you take, then you can do something like this. Take the last one. What does here it's 2ni, but doesn't really matter. Remove the last row and the last column, and then you subtract. I guess it goes like this, right? This one and that one, and it's equal to the determinant of the matrix itself without any removals times the determinant of the matrix where you remove the first and the last. Yeah, so all of these guys are determinants. So this is so-called Jacobi, Trudy, Lewis Carroll identities. Like there are 10 names associated to it. And claim is that you can rewrite it this identity, this matrix identity, as this relationship. And again, so this matrix M, its components will be some functions which either you can describe as Q polynomials from the QQ system or as sections of the Oper bundle, or just as components of the quantum zone spin. Okay, good. I think I should stop here. Are there any more questions?
Here, the identity that you showed is actually a special case of a larger class of identities where you take any known simple identity of determinants and just add a long tail. So for example, in this case, it's the identity that the determinant of 4 1-by-1 determinants, A, B, C, D, 1-by-1 matrices is a determinant of a 2-by-2 matrix. And then you can just add a tail of n additional rows and columns to each.
Well, you mean you represent each of those guys as a matrix, right? And then
yeah, I mean, so you add you can kind of add to n more columns and rows, the same rows, and so basically this you can have a generalization of this by adding a 3-by-3 matrix.
Will it be of higher order than, or like here's quadratic? Will it be
the higher order? So the next level will be a cubic identity of polynomial.
Interesting. Yeah, good. So do you have a reference I can look at? We have it somewhere. Because
I did it in a very old, many years ago in an old linear algebra book. I have no idea what the reference is, but if you let me share, I can quickly the screen. I can say what I mean.
Yeah, okay, sure. Let's do that. I think you need to or it needs to be a co-host. Because if it's the case, then other high order cluster identities can be also explained this way.
I think I can. But I cannot. Maybe I could just write on a blank screen.
Can you annotate on my screen?
Oh, yeah. I think let me see if I can do that. Options. I'm not sure if I can. Let me see what happens if it doesn't let me write. Let me try again to share. Okay, I think I can annotate on Mira's email. So I don't let's see if I can.
I need to quit my screen.
I need to get. Yeah, I think I can do.
Okay.
Yeah. So we look at this A, B, C, D. But think of this as an identity for 1-by-1 matrices, and then that equals A, B, C, D.
I'm sorry, I don't see anything. Do you guys see what is writing?
Oh, I'm not. Sorry, it looks like I'm sharing, but it actually.
Well, I'm gonna quit my sharing. Hold on. Yeah, I stopped mine. Yeah.
Okay, let's see if I can. No. Is that visible?
Yes.
Okay, so now I'll take the pen. Yeah. So here's the basic identity. These are determinants of 1-by-1 matrices. and on the right is a determinant of a 2x2 matrix. So now you kind of generalize it by writing something like that. So you kind of start with the bigger matrix, let's say A, B, C, D, F, G, H, something, and so on. And you replace that with the matrix that you get by, just dropping this column, but leaving all that stuff. And you replace that by what you get by dropping these two columns, but leaving that stuff. And then the statement is that you still get a correct identity, but you might have to multiply by the determinant of
by determinant of the thing that you removed. Okay.
Some power. And then that works also if you add more elements. So you can start with the identity A, B, C,
the star formula, right, for 3. Yeah.
In fact, the statement is that for any identity that you find for matrices like that, you can always generalize by adding a long tail. So a cubic identity has any meaning
Oh, interesting. Yeah. So it may be relevant to other identities that Fomin and Zelinsky have. So it would be nice to look at. Yeah. Thanks.
Thank you for this wonderful talk.
Thank you. In fact, yes, I think what Ori said, that's how you prove it. Like, if that's how you would prove this identity otherwise. Sort of, we gave a geometric interpretation for it. Yeah.
All right, any more questions?
Now we're working on the connection with ODIM, so where like there's an affine Oper for like G hat, and we think that there's a duality between affine Opers and q-Opers, like in terms of basically the kind of sister action that involved, like the sister action that we have on the q-Oper side is somehow traded for affinization on the other side. So
What's an affine Oper for you?
it's the like. You need to write this homomorphic Schrodinger operator. So it's like del Z plus some potential which has some whole structure. Otherwise it's just normal Oper, not the q-Oper. But then you would add some affine root multiplied by some other function. So you just look at the kind of differential operator like that.
See, I see. You just affinize the group.
Yeah. So like this text is in G, and this is the affine root. Okay.
All right, maybe we should
I
thank
think I need to go. Yes.
All right, thanks a lot. Thanks for the talk. It was really fun.
Of course, yeah. Like, see you guys later. Thanks. Bye.
Okay. Bye.
Next week, please. Bye.
Enjoy your holiday.
Thank you. You too.
Bye.